Okay, Humam, so if you have seen the notes, you will be able to get some points which are very important, right?
Yes, sir.
Okay, so we are going to have this cyclic structure of glucose, which is a very important point. Okay, you should know how to write the cyclic structure of glucose. Without cyclic, when you are going to see in that Fisher projection, you will be able to get that the uh, chiral carbon is 4. But in cyclic, you will see some changes that I'm going to tell you. So first of all, I'm going to show you. This is your aldehyde CHO that I wrote, and then there is OH, then there is H, then there is OH, and then again there is OH, and then we have CH2OH. After that, you can see H, H, OH, and then H, right? Now, how we are going to write the cyclic structure, that is very important. As you know that carbonyl compound, that means C double bond O. Oxygen is more electronegative, so it will take electron. Okay. Now, what you are going to do, I'm going to do the same thing here. It will be like this. That means this become negative, this become positive. One of the pi bond between carbon and oxygen will be dissociative. Now, this carbon is having only three bonds. So now what will happen? This carbon is going to attach with before that I would like to do this as well. The last chiral carbon in this is the last chiral carbon. This hydrogen is less electronegative, so positive, and oxygen is more electronegative, so negative. And what you are going to do, join this carbon. I'm going to show you. This will be something like this. And this positive is going to be with oxygen, OH it becomes, and then there will be H on the left hand side. The rest part is as it is OH, H, OH, and there is H, there is OH, there is H, and this last chiral carbon will be O because hydrogen of this is transferred to that, and then H, and here it will be CH2OH. Now, what you need to do is very simple. This carbon is going to bond with this negative to positive, positive to negative. Now you can see there is a cyclic structure. This carbon, this carbon, this carbon, this carbon, this carbon, and then oxygen. Are you getting my point?
Yes, sir.
So that means six-membered ring. Here it forms. I will explain it how. First, write it. This you need to understand how to write the cyclic structure.
Yes, done, sir.
Very good. Now the cyclic structure is basically known as Haworth projection formula, like Fisher projection. In the same way, this is known as Haworth projection formula. Now see what happens here. Very simple this is. You are going to first numbering. Numbering is very, very important. Now, if I'm going to number it from here, 1, this carbon is 1, 2, 3, 4, 5, and this becomes 6. That means 6-membered ring is there. And this is your heterocyclic. That means the corner atom is not only carbon, other than carbon is also present. So what I'm going to do, I'm going to write the structure something like this. Try to understand. Okay, this is the sixth, then this is the fifth, this is the fourth, this is the third, second, and this is the first. Are you getting my point?
Yes, sir.
Now, on the first carbon, try to understand. On the first carbon, if you are going to see OH on the right hand side and H on the left hand side. Okay. On the first carbon, OH on the right hand side and H on the left hand side. So you are going to write it like this. This OH on the right hand side, that means you are going to put it down. You are going to write it down. And left one will be written on the top. Okay. So this is the bond you are going to write like this, and this. On the second part, if you are going to see on the second carbon, OH on the right and H on the left. So again, OH will be written down and H left. On the third carbon, H on the right. So you are going to write down right. That means you are going to write at bottom or down. And left can be written as up. Okay. So on the third carbon, H, OH. On the fourth carbon, OH, right, that means down. And then H is here. And on the fifth carbon, if you are going to see the fifth carbon, there is no left or right. Yes or no? So for fifth carbon, you can see H and CH2OH is there. Are you getting my point?
Yes, sir.
So we are going for this type of scene, you are going to give preference to molecular weight. So you know that molecular weight of CH2OH is greater than hydrogen. So this CH2OH will be written on the top and H will be written on the top. Are you getting my point?
Yes, sir.
Basically, this is how we are going to write the cyclic structure of glucose. Cyclic structure of glucose. Okay. It's very important to do the numbering while writing. Just wait a minute. Oh, what is on this OH and H? Okay. Now its name is alpha. Then comes your D. Then comes your positive. Then comes your glucopyranones. I will explain each one of them. Very important it is. Glucopyranones. First of all, alpha. Basically, there is isomer, alpha or beta. Two isomers. Two isomers. If H left, that means it is known as alpha. If H is on the right hand side, that is your beta. D, D is for this D is different than a small d. Last chiral carbon, if you will see in Fischer projection, last chiral OH on right. If last chiral carbon OH on right side, then you are going to write a D. Otherwise, it will be capital L. Positive, you already know, we use this for dextro and glucopyranols. Gluco, that is for glucose, and pyranols, basically this represents the structure pyranols, pyrene. This structure represents pyrene. So that's why this is your para. So that's why para. Is that clear?
Yes, sir.
Please do write. Let me know when you are done with this. This H we are talking about the first carbon. You can see the first carbon having H on the left. That's why it is alpha. And if you are going to change the position H to the right hand side, it will be beta. And on the last chiral carbon, OH or H, if you are going to change, that will be your capital D. Please do write it. Let me know when you are done with this. Are you done with this?
Yes, sir.
चार्ज हो रहा है? Very good. Now see, I'm going to write the beta phase shift projection for beta. So this is your H, this is your OH, then this is your OH, this is your H, this is your OH, this is your OH, and this is your CH2OH. H, H. Okay, can you write the cyclic structure of this? Let me know when you are done with this. This chapter is very easy. We will do the cyclic structure of fructose as well. So you just need to do the numbering first. 1, 2, 3, 4, 5, 6 is there. Okay, one mistake I have done here is that this I should be connected like this. Okay, yes or no?
Yes, sir.
Are you done with this?
Yes, sir.
Okay, so just match it. I'm just going to draw the structure O like this. You know the numbering I started from carbon. This carbon. So on this carbon, hydrogen is on the right hand side, and what we are writing, whatever is on the right hand side, that is on bottom, and OH on the left. On the second carbon, OH on the right, OH is here, H on the left, like this. On the third carbon, hydrogen will be here, OH will be here. On the fourth carbon, OH here and hydrogen. On the fifth carbon, you can easily see that on the fifth carbon molecular weight, we are going to do preference, we are going to give preference, and hydrogen will be there. Now in cyclic structure, if you are going to see, this is also your chiral, this is also your chiral, this is also your chiral. That means basically in cyclic structure, we have how many chiral carbon? 5. And now its name is beta because on the first carbon hydrogen comes on the right hand side. D because on the last chiral carbon, just wait a minute. Okay. Okay. So we write D as you can see OH on the right hand side on the last chiral carbon, and then plus because it's a glucose, and then we can write glucopyranose. Pyranose because it is similar to pyran, and gluco because it's glucose. Is that clear? Now there are some points that you can go through. Alpha and beta are known as anomers. Alpha and beta are known as anomers because what is anomers? So basically, on the first carbon, there is change. On the first carbon in alpha, if you are going to see, OH is on the bottom and H is on the top, right? So this is called C1 anomer. What it is called? C1 anomer. Basically, this is switching position. Are you getting my point?
Yes, sir.
Switching to position. The rest will be as it is, but on the first carbon, there is switch. HOH, that is your anomers. Okay. Anomers are diastromers. That means they are not mirror image of each other. Next point is all anomers are diastromers. That is confirmed. But all diastromers are not anomers. Are you getting my point? You know that if you are going to take two different compounds, that will be diastereomer, not mirror image of each other, but it is not necessary that they will be anomers. Are you getting my point?
Yes, sir.
Okay, so please, is that correct? That did you draw this correctly?
No, sir.
Okay, so if there is any problem in this, just let me
No, no problems.
know. Okay, can I change the slide or you are writing?
Yes, sir, you can change my room.
Cyclic structure of fructose I'm going to show you. As I told you, in fructose and glucose, you know the chemical formula are same, but they have different functional group. In glucose, we have aldehyde. In fructose, we have ketone. So first, I'm going to write the Fischer projection of fructose CH2OH, and then there is C double bond O, and then we have this OH. Sorry, in this we have HOH. Then comes your OH, H. Then comes your OH, H. I told you to draw Haworth projection. What you need to do, first of all, carbonyl compounds will be like this. There will be negative, there will be positive. And now on the last chiral carbon, this is your chiral carbon, so positive, negative. And what you are going to do, this is your carbon. So I'm going to draw the carbonyl carbon here, and this will be CH2OH. That is connected with this, and this becomes O. With O negative, H plus will come and it becomes OH. The rest part will be as it is. You can see H is on the right hand side, OH on the left hand side. OH on the right hand side, H on the left hand side. And then only O left on the right hand side and H is there. And this will be connected with each other. Okay. And then there is CH2OH. Now, can you try this? Now, one more thing I want to tell you is that if you are going to see the chiral carbon, can you tell me the chiral carbon in this picture projection? How many chiral carbon present in this? How many chiral carbon in this compound without cyclic? So you can see this is not chiral. This is also not chiral because it is sp2. This is your chiral. This is also your chiral. This is also your chiral. This is not chiral. So chiral carbon or chiral center in this is your 3. Yes or no?
Yes, sir.
But if you are going to look into this, isn't this chiral? Isn't this chiral? Isn't this chiral? Isn't this chiral? Now the chiral in a cyclic structure will be equal to 4. Yes or no? This will not be chiral. This will also not be chiral. Are you getting my point? Total chiral carbon in cyclic structure of fructose is 4.
Yes,
Total chiral carbon in Fischer projection
mm,
formula of fructose is 3. All is it is written. Everything is written there.
yes, sir, got it.
Oh, let me know, then I will draw the structure.
Done, sir.
Done. Okay. So if you are going to look this carefully, so it will be one, two, three, four, five. Five-membered ring is there. In the previous one, we got six-membered ring. Yes or no?
Yes, sir.
So what I'm going to do, a five-membered ring, which is heterocyclic. Carbocyclic or homocyclic is the one which is having carbon atom at the corner, right? Now you can see, I draw this at one. Let's say this is your one. This is your one, two, three, four, and oxygen is your five, right? Now the same thing you are going to do either from this side or that side, that will be same. Just wait a minute. I should not do numbering like this. Just wait a minute. So how can we do this? Okay, very simple. So should I do this? Okay. Now on this OH on the right hand side, that means it will be written on the bottom, right? And CH2OH on the left hand side, that means it is written on the top. In the same second, you can see hydrogen will be written here, OH will be here. In this, you can see OH will be written here and H will be written here. And at last, you can see this carbon again follow the molecular weight. So you will be getting CH2OH and then, are you getting my point?
Yes, sir.
And this has a name alpha D. This is your levorotatory. If you remember the preparation of glucose in which we hydrolyzed the sucrose. So we got fructose as L, fructofuranose. Its full name is fructofuranose only because it is alpha, because on switching position OH on the right, if it is going to be on the left, then it will be beta. I will let you draw. And D because last chiral carbon, if you are going to see, or you can see in this OH on the right. If you want to switch on the left, then it will be L, capital L. Negative because it is levorotatory, fructose because it is fructose, and furanose because it represents furan. Furan and furan has a structure like this, similar to this. That's, please do right. Let me know when you are done with this.
Yes, sir. Done.
Hmm. Now I'm going to give you alpha, we did, beta I'm going to give you. Now I'm going to switch this to CH2H on the right hand side. Previous one, we had OH on the right and now we had a OH on the left. Now this is your OH, this is your OH, and this is your O. H is there, H is there, OH is there, and then CH2OH. Now you are going to draw this. This is connected here. Please draw this. Are you done with this?
Yes, sir. But I'm not sure if it's correct or not.
Okay, no problem. See, again, you are going to do this. 1, 2, 3, 4, you can do anything. Like, first, I'm going to do like this. After this, on this carbon, you can see CH2OH is there. So on the right hand side, that means it is going down, right? CH2OH and OH on the top. Then H is on the bottom and then OH is here. Then again OH on the bottom, H will be on this. And then you are going to follow the molecular weight, you will be getting this. Isn't it right? Have you done it correctly or not?
So it's just HO I put down for H.
So you have to be
It is in.
careful in your words. You are going to write whatever is on the right. You are going to write on bottom, right?
Okay.
Or below you can write. And if it is on the left, then you are going to write on top. Okay. Or you can write for this last carbon as well. There is no right or left, so you are going to give molecular weight the preference on top. If OH is on the left hand side, then it will be beta. D is that, and then negative, and then it is fructofuranose. Now the next one, which is very important to us, is that if you are going to switch the last chiral carbon, like OH is here, last chiral carbon to this, it becomes L, not D. So please do write it.
Yeah, done, sir.
After this, if you are going to see, there are some points about alpha and beta forms are called anomers. And here you can see this is your second carbon. If you are going to number it, you have to do it from this, right? You cannot directly jump to any carbon directly. So this is your 1, 2, then 3, 4, 5, and then 6, right? So this is your C2 anomer, which is very important to remember. They can ask you directly which type of anomer glucose is, that is your C1, and this is your C2. All diastomers are not anomers, but all anomers are diastomers. Okay, is that clear, mom?
Yes, sir.
Now then, again come muta rotation. Muta rotation is basically equilibrium between this alpha and beta form, that is called your muta rotation. Okay, can I change the slide?
Yes, sir.
Okay, see. A structure of sucrose. When you are going to talk about a structure of sucrose, you know the formula C12H22O11, and it is a disaccharide. Disaccharide. Disaccharide means any answer?
No, sir.
Now disaccharide, you should remember di means two. After hydrolysis, if you are going to do hydrolysis of sucrose, you will be getting two monosaccharides. It's very simple. This chapter is purely theoretical. Apart from that 9 reactions, please go through that again and again. So since this is your disaccharide, that means you are going to add it to after hydrolysis, you got fructose and glucose. That means if you are going to add glucose and fructose, you will be getting sucrose. So if you are going to add alpha D glucose plus beta D fructose, then you will get then you will get sucrose. Then you will get sucrose. I'm going to draw the structure of this alpha beta alpha. This is your this is the scenario. H OH, then comes here OH, H, then comes your HOH. You have to understand the concept. Basically, there are rules that you need to follow and keep it in mind in order to do it correctly. This is your alpha D glucose. Now, if I want to draw beta D fructose, that we already did. So instead of remembering this, you should go through the concept and the rules and then draw it. And then beta D fructose, I'm going to show you. It is something like this. This is your OH, this is your H. Then comes here, H is here, OH is here. Then comes here, H is here, OH is here. Then at last, we have this H and CH2OH. Now, you know that when you are going to hydrolyze mixed water in sucrose, then you will be getting this and this. Okay. So in this step, what you need to do, remove water. Remove water after combining this. So how I'm going to remove? I'm going to take this H and this O. So what we will get is very simple. This is how glucose looks like. This is your OH. This is your H. The rest part will be as it is. Whatever is given in the question, you can see. H is there, OH is there, then H is there, OH is there, then OH is there, H is there, then H is there, CH2OH is there. Now there is no OH. Basically, I removed hydrogen from here and OH from the next one. So I'm going to write it. Look at this carefully. This is now connected with this, and we have CH2OH. The rest part is as it is. H was there, OH was there. So if OH is there, that means H is there, OH is there, and then again 2OH is there. Now they are connected, and this is the structure of sucrose. This is the structure of sucrose. And if you remember, this is the carbon 1 in glucose, and this is the carbon 2 in fructose. So I'm going to write it this 1 and 2. And this linkage between this glucose and fructose is known as glycosidic linkage. So question can be directly asked, glycosidic. Please write it carefully. This is called glycosidic linkage. They can ask you where is present this glycosidic linkage in sucrose. So basically it present between C1 and C2. Is that clear? So this is your monosaccharide. This is also your monosaccharide, and they are connected. They are connected with oxygen O, and this linkage is called glycosidic linkage. Are you getting my point?
Yes, sir.
First, write it. Let me know when you are done with this.
Done, sir.
Now see, I told you the position of glycosidic linkage they can ask you. So you can write this glycosidic linkage is present at C1 and C2. I told you, right? So write it. Then we will go for structure of maltose. You can easily understand how you will get alpha D glucose, alpha D glucose. Then remove water. Then you will get O linkage O between them, glycosidic linkage, which is in between C1 and C4. Can you see the notes? First write it, then let me know. Humam,
Yes, sir.
so can you see the notes of the structure of maltose?
In the PDF which you sent.
Yes, yes.
Yes. 1 minute, sir. I'll remove the PDF. Yes, sir. I have the notes.
Okay, maltose. Check for maltose, structure of maltose after glucose. Page number 17 or 18.
Yes, sir, I got it.
Yeah, this is very easy, right?
Yes, sir. It's easy.
Structure of lactose. Actually, it is given that alpha D glucose, alpha D glucose. So you just need to, for maltose, if you are going to see, this is how you are going to do it. Take this. The rest part will be as it is, alpha D. And you know that there is OH and there is H. And then the fourth carbon, there is same thing. So you just need to remove this H2O. You just need to remove this H2O and connect oxygen with this. So it will be something like this. Oxygen is connected with this. Are you getting my point?
Yes, sir.
So glycosidic, this is your C1, this is your C4. So it's very easy, right? In the same way, if you are going for lactose, lactose is also very easy. In lactose, you need beta D glucose. Again, the glycosidic linkage is in between C1 and C4. That is important. They can ask you directly. Okay.
Okay, sir.
One of the compound that is your after lactose, we have a starch, which is a bigger structure, but it's also very easy. A structure of a starch. A structure of a starch I'm talking about. And if you are going to see the structure of a starch, there are two components in this. The first one is amylose and another one is amylopectin. What is this amylose and amylopectin? So it's also very easy. A starch is polysaccharide, as I told you. It is polysaccharide and also it is non-sugar because they are not sweet in taste. So this is your polysaccharide. And it has a formula C6H. 10O5 whole n, as you know that we did this. And if you are going to do the hydrolysis of this, you will be getting several units of glucose C6H12O6. So to draw the structure of a starch, there are two components. One is amylose, another is amylopectin. What is the difference between this amylose and amylopectin? This we should know because it's very important. Now see, what is the difference? First of all, this is linear polymer. That means in a straight line type, linear polymer of alpha D glucose. That means basically you have alpha D glucose which is linearly arranged, connected with each other. The next here, if you are going for amylopectin, this is your branched polymer. Branched polymer. There is branched, okay, linearly going, and there will be branched polymer of alpha D glucose. There is branched in this, and whereas in amylose it is linearly arranged. The next is in amylose only 15 to 20% starch present, only 15 to 20%, and in amylose 80 to 85% starch present, 80 to 85% starch present. The next one is this is your water soluble. It can be easily soluble in water. And this is your water insoluble. These are all written. This is very easy. And here the glycosidic linkage is very important. Glycosidic linkage is your C1 and C4. This is C1 and C4. And here, since branch is there, so be careful. Glycosidic linkage at C1 and C4. C1, C4, glycosidic linkage and branch at C6. Branch at C6. I will show you. So please do write this, then we are going to do it. Let me know when you are done with this. Mom, are you done with this?
Yes, sir, done.
So first we are going to draw the structure of this amylose, which is linear polymer of alpha D glucose. So, and then we will connect that amylose. So two types of component is there, amylose and amylopectin. So you can see in this alpha D glucose linearly arranged. I'm gonna show you. There will be several units of this. Now alpha D glucose, you know that this is your OH, H, OH, H, OH, H, OH, H, OH, H, OH, H, and like this. Several units will be good. Now, what you need to do, remove water molecules. So what I'm going to do, since it is polymer, so I'm going to draw it like this. Now, you know that what you need to do, I'm going to remove H from here. Basically, you need to remove water molecule. So how I'm going to remove water molecule? This water molecule, this water molecule. You can remove this as well, whatever you want. This water molecule, this water molecule. So it will be like this, something like this, or something like this. Something. Okay. So what you will get is very simple. You will be getting this. This is the basically structure of amylose, in which you can see there is oxygen. So it's just the representation that I'm writing like this. Otherwise, O can be here as well. Now I can write hydrogen is there. Just wait a minute. Let me draw all the time. So four times I took. So four times I'm going to draw like this. Now you can see this is your hydrogen. This is everywhere hydrogen on top. So hydrogen is on the top as it is, as it is, as it is, as it is. Now what you need to do? This there is oxygen glycosidic linkage. This is if you are focusing on this, this is your C1 and this is your C4, right? So that's why glycosidic linkage I told you that reside between like this. If you want to, it don't be not make you confused. I can write like this for it, and I removed this H from. Okay, so basically you can see this is your glycosidic linkage and also known as alpha link. Why alpha link? So because it is alpha glucose, that's why we call it alpha link. Very simple.
So could you explain again, please?
See, what is amylose? Amylose is linear polymer of alpha D glucose, right? Linear polymer of alpha D glucose. Yes or no?
Yes.
Now, what is linear? Linearly, they are arranged alpha D glucose, right? So this is what is alpha D glucose, alpha D glucose, alpha D glucose, alpha D glucose. This is right. Now, to make the structure of this starch or amylose, you need to remove water molecule. So I removed water molecule from this. This is basically polymer, not one unit, two unit, three unit. Many units are there. So if I'm going to remove this water molecule, oxygen between this and this will be left or not? Yes or no?
Yes.
So since this is polymer, this is what you need to repeat. Again, I removed water from here. Now oxygen between this and this too. Again, I removed water from here. If you want to write it 20 times and then remove 20 molecule of water, doesn't matter. 3 times, 4 times, 5 times is enough. Okay.
Okay, sir.
What is glycosidic linkage? This is your mono. This is your mono, which is connected with this oxygen. This is your glycosidic linkage. In this, you can see C1, and in this, you can see C4. So the glycosidic linkage is between C1 and C4. Write it. And this link is also known as alpha link because it is alpha glucose.
Yes, got it, sir.
Very good. So this was about amylose. Now we are going for amylopectin. Now amylopectin already told you that this is branched. Okay. So I'm going to write something that is already with you. Branched polymer of alpha D glucose. Branched polymer of alpha D glucose. And the glycosidic linkage, in this case, we also called it alpha links. Glycosidic linkages, that means alpha links, are present here, present at C1, C4, and branch at C6. Branch at C6. This is already we understood in the previous one. All I need to do, basically, C1, C2 is this will be in a line, and there will be at C6 there will be a branch. So I'm going to show you. Okay. Now there is another. I'm going to write it. Now you know that this H and this is your OH. OH. Okay. This is your OH. Just wait a minute. Let me see. Okay. This is your HOH, and the rest part will be as it is. And this is your CH2OH and H. The rest part will be as it is. This is also your alpha. This is also your alpha. Now you know that this is your carbon 1, and this is your carbon 6. So as I told you, there is branch between C1 and C6. So what you need to do, remove this water. Just wait a minute. My laptop is about to. Am I audible? Mom.
Yes, sir. Yes.
Now you can see this is your first carbon and this is your sixth carbon. So, and this is your first carbon. So here you can see glycosidic linkage alpha links are present at C1 and C4 that we did in the previous. They are together and branched at C6. C6 you can see you are going to remove this water and what you will get is very simple. This is the scenario that we got. Now there is oxygen and then there is, sorry, not oxygen only, CH2O is also there. So we can write CH2O and the rest part is as it is. And this is your branch at C6. So what is amylose? It is linear polymer. And what is amylopectin? There is the sixth carbon, sixth. Just below that, there will be alpha D glucose, which will be connected with the bottom one, C6, sixth carbon, and first oxygen. Very simple it is, right? Branch at C6. If this will be wrong or something, just wait a minute. Just wait a minute. I should write, like, not this. That will be wrong. Just wait a minute. Just wait a minute. I should write, like, not this. That will be wrong. Just wait a minute. I should write, like, not this. That will be wrong. Just wait a minute. Just wait a minute. I should write, like, not this. That will be wrong. Just wait a minute. I should write, like, not this. That will be wrong. Just wait a minute. I should write, like, not this. That will be wrong. Just wait a minute. I should write, like, not this. That will be wrong. Just wait a minute. I should write, like, not this. That will be wrong. Just wait a minute. I should write, like, not this. That will be wrong. Just wait a minute. I should write, like, not this. That will be wrong. Just wait a minute. I should write, like, not this. That will be wrong. Just wait a minute. I should write, like, not this. That will be wrong. Just wait a minute. I should write, like, not this. That will be wrong. Just wait a minute. I should write, There is first CH2 and then comes here oxygen. Oxygen. Write it like this. So let me know when you are done with this. Let me know when you are done with this.
Yes, done, sir.
Okay, the last one is also very easy. If you are going to see, that is your structure of cellulose. This is your polysaccharide. And what it is basically linear polymer. It is just like amylose, linear polymer of beta D glucose. Beta D glucose, not alpha. If you are going to take linear polymer of alpha D glucose, you will get amylose. Okay. Now, here, this is important glycosidic linkage. Glycosidic linkages. That means beta links here. Because beta links, why? Because it is beta glucose, that's why, are present at C1, C4, between C1, C4. I can draw the structure which is very easy. This is your beta D glucose. I will write to the branches, then you will come to know, understand easily. Now you can see that this is your HOH. Now this is your OH. This is at fourth carbon, there will be opposite if you are going to see. This is the structure of beta D glucose. Beta D glucose. Beta D glucose. These are all beta DP. Now see, in order to draw the structure of this cellulose, you need to remove this H2O. So this is how I'm going to remove this H2O. I'm going to remove this H2O. I'm going to remove this is H2O. I'm going to remove. In the same way, this H2O I'm going to remove. In the same way, this is with someone else, with something else, because it is polymer we are talking about, right? So many will be there. So this is how I'm going to write the structure, final structure. 4I2, 1, 2, 3, and this is your. Now see, hydrogen is there as it is. Hydrogen is there, but they are connected with a link that is your port. So to look beautiful only, I'm going to write the bond like this. Okay. Again, hydrogen will be here. For this, hydrogen will be here. For this, hydrogen will be here. And there is O, there is O. So I'm going to write it like this. Okay. Now again, hydrogen will be here. Hydrogen will be here. You can easily understand how easy it is. You just need to remove both. For the last carbon, if you are going to see, it will be there is hydrogen like this, and there will be something like this, which is going to. For this, you can see one hydrogen is there, and it is going to be like this. And if you are going to check the glycosidic linkage, this is your beta link only because it comes from beta glucose. So this is your beta linkage, and this is your C1, then this is your C4. So please do it.